We go on a bit more till lab 10, and then we stop for having lunch. Because I'd like to finish this second part about input-output before lunch. So lab 7 is about 7-segment displays. The original SOC also has support for the 7-segment displays. We first explain how the controller works. It's an ad hoc controller that we built ourselves for this board. So this is not from open course. It's created by ourselves. As usual, we analyze the high-level specification and the low-level implementation of this controller. So this controller is quite simple. It includes an enable register and a digit register. So the specification is quite simple. The enable register determines which of the 8 digits is enabled or disabled. Note that it's low asserted, so 0 means that a digit is enabled. And the digits register specifies the value to show in each of the digits. So for example, if I write FC, which is 1111100, I'm saying that I want to enable the 2 rightmost digits and disable the remaining 6 digits. And if I write a 7 and a 1 to digits reg, I will write a 7 here and a 1 here. So this is the assembly code for initializing the 2 registers with those values. And this should make the 7-segment display show 71. Okay? This is an exercise which is proposed in this lab. And there are others, such as showing the value of the switches on the 4 rightmost digits of the 7-segment displays, which is the exercise that you were running, or showing the string 0 to 8 moving from the right to the left. And also, we we propose some advanced exercises where we modify the controller. So the original controller can only show hexadecimal digits, from 0 to F. And we want a controller which can show any combination of on-off LEDs. Okay? So we first ask the user to modify the controller, and then we ask them to display any message, such as I say hi, or something that can be represented in a 7-segment displays. Okay? Well, as for lab 8, it's about timers. We use the timer module from open course, linked here. And this can generate precise timing. So we'll create the delays not with a for loop, but with a timer, which is much more reasonable. But we'll also include advanced features such as PWM for controlling the speed of a motor, the brightness of a light, or whatever thing we want. In the lab, we again first describe the high-level specification of this controller. Then we ask the user to include PWM functionality to control the tricolor LED available on the board. Okay? This board has an LED which can switch color by using a pulse width modulated signal. Okay? So we ask students to first include this capacity and then program the tricolor LED. You have it in the solutions as usual if you want to take a look. Yeah, this is what I was just saying. Lab 9. This one is very interesting because so far we've been using polling for communicating with the peripherals. But here we introduce interrupt-driven input-output. We first explain the differences between each of the between interrupt-driven and programmed input-output. We then explain how the interrupt controller included in RVfpga. We explain how to configure interrupts using Western Digital libraries, PSP and BSP. And finally, we ask for some exercises. Well, I'll skip this one. It's just the introduction. So this is the interrupt controller included in the core. And it has two interrupt lines, one coming from the GPIO, from the switches, one coming from the timer. Okay? So in this lab, we'll create an exercise that uses these two interrupt sources in order to perform some functionality. Okay? You have the specification, the exercise description in the document. You can read it. And then we'll modify the SOC in order to include as a third interrupt source coming from the buttons. This is not supported by the original SoC, but by the extended SoC. Okay? And some exercises working with this extended version. I suggest that you do, but this we can do it before, after lunch, a hands-on activity using interrupts. So you'll compare a program using polling and the same program using interrupts. Okay? You have the guidance for this in the documentation, but as I was saying, we can do it after lunch. Let me finish now with Lab 10, which is about serial buses. We first describe how common serial buses work, UART, SPI, I2C. And then we focus on the SPI accelerometer available on the Nexus A7 board. So we explain how SPI works, we provide an example, and we ask students to work with the accelerometer. As usual, we then ask for some low-level analysis and advanced exercises. To finalize, before lunch, let me show you a demo of the use of the accelerometer, which you can test later if you want. So in Lab 10, okay, for this I need the board, so let me show the board here. So let me open the project that contains the solution for this exercise using the accelerometer. It's available in the solutions folder. Lab 10, so solutions for Lab 10, it's here. It's the accelerometer example. I open it in Platform.io. Note that we are going to use the original, the basic SoC, which is already programmed on the FPGA, so we can just run the program on the board. The program asks the user to print on the 7-segment displays the value of the X, Y, and Z components of the measured by the accelerometer. So if you execute it, you'll see how those values are shown in the 7-segment displays. If I move the board, you'll see how they change. That's the basic exercise proposed, but you can then include more things such as, well, whatever. You can use the accelerometer data for using it for something else. Okay? Well, with this, we finish this initial 10 labs. For labs 11 to 20, it's different things that we'll do there. We'll explore the core internally by using verilator simulations and performance counter measurements. We'll cover that part after lunch. So let's stop for, I don't know, 45 minutes or 1 hour, whatever we need.